I'm actually really excited to give this talk because Cosmic Engine just encompasses a little bit of everything. And, that's why I became a scientist in training, is because I had all of these questions and I wanted to figure out how to answer them, right? So some of the questions that we're going to talk about today are just going to involve questions of how does the universe transform elements into other elements? How do stars form? And how do they evolve, right? And these are all, different questions, but they really kind of tie in together. So to kind of give you a bit of a update or a hint on what I do, I went through my Facebook feed and looked for some science related photos that I uploaded as I've been doing research for the last 7 years. So I originally started in Eastern Europe. So I grew up in Romania, where I went all the way through 8th grade, and then I moved to the United States, where I did high school and university. And as I was going to university, I knew that I wanted to do science, but I didn't really have a lot of exposure to like what science really looked like, and I didn't really know any scientists. My grandfather had worked as a chemical engineer, so I was familiar with sort of laboratory settings, but I had no idea what astronomers did. So because I didn't know how I wanted to pursue some of these questions, I decided that I was gonna just take on a lot of work, and I did a degree in physics and one in astrophysics. So for my degree in physics, I worked with something called the Cryogenic Dark Matter Search Program. And there we work with super low temperatures using liquid nitrogen and just really complex systems in order to look for dark matter. And with my astrophysics degree, we work with computer simulations to really understand how future space telescopes will be able to give us a picture of the universe. And the really cool thing about science is that even if you do something that sounds really specific, as you move on, you can get involved with different projects. So that shadow selfie there is from a program that's run from Swinburne called Deeper, Wider, Faster, where they're looking for these, these unknown fast radio bursts, and they're trying to put together 20 different telescopes to really understand what they might be. And that's just something that I happen to do on the side. My research now focuses on, if you search for a lot of things, the coolest thing in astronomy is going to be a black hole. So do you guys know what black holes are at all? You can raise your hand if you know. Let's see if I can see it. Is that a yes? It's a little tiny on my screen. So, of course, black holes are really, really cool because we don't really know exactly what they are. But one of their interesting properties that they have is that they have lots of mass, right? So because of that mass, they attract other things around them. So in this case, this is a kind of a smallish black hole, I would say, and it's pulling in a star. But they can be everywhere or nowhere. Do you guys know where you can find a black hole? So this time I'm going to need a volunteer to say if they know.
In the center of our galaxy.
Perfect. So this is actually the slide I was going to have, right? So so here I have a picture of Sagittarius A, and we think that little blob there is a black hole, not because we can see the black hole itself, but because we can see the way that gas and stars rotate about that point in space. But black holes can be they can be small, resulting from the death of a star, supernova that's a star that's larger than our sun. But they can also be quite large, and they can be so large that they dominate the galaxy, right? So when you have a very large black hole that's surrounded by lots and lots of gas, the black hole is trying to eat that gas, but even though it's a black hole and it's growing the more it eats, it can't take in all of the gas at the same time. So that gas gets heated, and as it gets heated, it radiates light. So what happens is that it creates the system called a quasar. Have you guys heard of a quasar before? Is that a yes? No? Okay. So the really cool thing about quasars is that, a black hole you can't see because it's, nothing can escape. There's no information coming beyond the Schwarzschild radius. But what's really cool about a quasar is that it's actually the complete opposite. These are some of the brightest things in the sky. So that means because they're so bright, we can see them from very, very far away. And really, that's what my research is, and for my PhD, is that I look at the light that's emitted by quasars, and as it travels across the universe, it interacts with the stuff between galaxies, and even with galaxies, and those interactions leave little barcodes in the light. So what I do is I look for those barcodes in order to understand the stuff that's in between galaxies, the intergalactic medium. So that's the kind of definition of a quasar. You have a superheated gas surrounding galaxy, but really it's a system. So you have to remember that in order to have a quasar, you need to have a really big black hole, and then you also need to have lots of gas that's being excited through centrifugal because it's being rotated. So I mentioned absorption systems, so that's the stuff that happens along the line of sight. So the nice thing about it is that each individual element has a little barcode. So the way it works is that the quasar emits that rainbow of light that you see on the left, right there. So that's the light source. And as the light source goes across the universe, it interacts with something. And depending on what that something, that absorbing material is made of, it leaves in these barcodes. So understanding these barcodes really lets you know the chemical properties of that absorbing material. So it goes backwards, right? So, this is a quasar, and I'm going to play a little movie next just to kind of give you guys an idea of what this looks like in practice. So here we have a quasar source, and when I turn on when the light leaves, see, it interacts with little clouds of neutral hydrogen, and it travels across the universe, and nothing much really happens for some time, and then it gets close to a galaxy. And did you guys see those absorbing material? So let's get it back a little bit. Let's pause it. So as it goes as it goes close to the galaxy, let's see if we can get it. There it is. You see how there's those absorption lines sort of come into play just to the right, and so that means that we can see that galaxy even if we don't actually see it. And what's really great about this is that we can take an account of all of the stuff in the universe by understanding these absorption patterns, right? So the absorption systems, which is the stuff that I work on, gives information on the stuff that's in between us and the light source. But of course, the light source itself is really interesting, right? So the emission lines, that's the information on the light source. In my case, that's a quasar. But what about our sun? So I don't know, is it cloudy where you guys are at? Yeah, it's overcast here as well. So, but I'm sure you guys have probably seen the sun before. So can you tell me what color it is? So it can be many different colors depending, right? It can be a sunset, it can be rising. But if you are in space, it would look mostly yellow. Do you guys think that the sun is a really big star? No? Oh, that's good. Is it really small?
No.
Okay. Well, what if I was to tell you that if you were to weigh up all the stuff in the solar system, 99% of the stuff, if you count up all the Martians and all the humans and all the comets and all the ice, that makes only 1% of the solar system. So 99% of the baryonic matter in the solar system is in the sun. Would anyone change their answer? So let's have another final show of hands. So knowing that 99% of all the stuff in the solar system is in the sun, do you guys think that the sun is a big star?
Is it a big star compared to?
It's not a big star compared to the other stars.
Perfect. You guys are thinking like scientists. I didn't give you a frame of reference. So, so yeah, of course, it's really big if we compare it to the Earth, right? We're big if we're comparing to an ant. But when it comes to other stars, it turns out that the sun is actually quite average, right? So it's just a collection of gas, and that gas is trying to fall in. That's what we call gravitational collapse. And there's some stuff inside called nuclear processes which support it. And that's a star like many other stars. Like that's actually just the definition of a star. And our sun is just one of those many stars, and it's actually quite average. I skipped slides. So I was going to ask you guys if you know what the sun is made of without giving you the answer, so I'm going to go back. So do you guys know what the most common element inside of the sun?
Hydrogen.
Okay. You guys have done your reading, so all right. So it turns out that like 98% of the sun is made of hydrogen and helium. And of course, there's other stuff, and the other stuff is really interesting as well, because we're thinking about the history of the universe, so we're thinking about the history of the solar system inside of that, right? So the sun wasn't always there, and it won't be there forever, right? So there was a time before the sun, and there will be a time after the sun. Do you guys know what the lifetime of the sun is? So you don't have to be exact, but yeah, just to the closest billion years. Is that how old it is, or how long it's going to live for?
Remaining life.
Remaining, isn't it?
Remaining.
Yeah, so I heard remaining life in there. So it turns out that it's about halfway through. So it's going to live about 8 billion years. But do you guys know how? So that means that the sun formed about 4 billion years ago. Do you guys know how old the universe is? So it's fair to say that it's more, right? Yeah. So the universe is older than the sun. Well, it turns out that all that rest of the stuff that I've highlighted there, if you travel back in time into the early universe, that ratio is going to be different. So that means that by tracing the rest of the stuff, not the hydrogen and the helium per se, but the other things like carbon, magnesium, silicon, is going to be able to trace the history of the universe. And that's really interesting because if you understand that, then you know how much of something, like how many supernovas happened and all of these other things. But of course, like we just answered a question with possibly like creating 10 more questions, right? So that's how science works. So let's ask a specific question, right? But it's kind of a complicated one. Like, what is the history of the universe? And have you guys watched the Big Bang Theory TV show?
Yes.
Okay, so to those that have, do you ever pay attention to the introduction?
Yes.
Right. So it's really cool. I mean, it's really cool that the history of the universe has now become part of pop culture, right? So you have 14 billion years ago, the universe was a hot, dense field, right? So if we put that sort of introductory song from the Big Bang Theory into a single poster, it'll look something like this, right? So we have the Big Bang, then we have this inflation, then we have cosmic microwave background, then the first stars formed and galaxies evolved. But really, it seems like a really intricate, in order to answer this big question, we have to answer like smaller questions along the way, right? So if we're going to talk about galaxies and metals and all that stuff, we really have to understand how is it that stars form, right? So let's start with that one question, right? So, and then of course, stars seem to be different, right? So then we have to ask, how do they form, and are they all the same? Right, so when you ask these questions, and whenever you have a question, you have to go and do an experiment, right? So in order to do experiments, you need to have instruments, right? If we need to figure out how fast you're going to run the 100-meter dash, you need a timer, right? You can't just go 1 1,000, 2 1,000, because you'll be running, and your sense of seconds will be different. So the really cool thing about astronomy is that our instruments are really cool, right? So I'm sure if you guys have heard of the Hubble Space Telescope, right?
Yes.
Yeah. It's a telescope in space that is able to take images of distant places in the universe. And just to kind of give you guys an idea of the scale, that's an astronaut, right? I don't know how big your screen is, but that's an astronaut. That's really cool. And just to give you an idea of how big the camera is, that's it right there. So it's pretty cool. And having something like that allows you to take really great pictures of different places in the universe. One of the really famous ones is something called the Pillars of Creation. And it really goes back to this idea of where do stars form. Because it turns out that stars form as families of stars. A star is not going to form just by itself with no other stars around. So generally, stars will form in nebula, which are going to be where they will form families of stars that are born around the same time. So this is a really famous picture of the Eagle Nebula. And in the left panel, you have that same picture that was taken in 1996, and you have the higher resolution now, and that was released in 2014. So it turns out that stars like to form in groups of stars, and when those stars form, what we do is we put them in we take their family portrait. So when we take the family portrait of a group of stars, a tool that we use to understand something about that family of stars is something like the HR diagram, right? So if you were to take, so who has been a part of a family group photo? Right, so you have grandma and grandpa, and then some cousins and brothers and sisters, and you can ask questions of like how many teenagers are in the family, how many grandparents there are, so then you can kind of get ideas about the family itself, right? So we do the same thing with stars, but the way we separate them is using something called the HR diagram. So no worries, I'll talk more in depth about the HR diagram. So on the y-axis, we have how bright something is, and then on the x-axis is the temperature of that object, right? But if we're taking a photo, how do we know the temperature? Have you guys ever used an infrared camera?
Yes.
Yeah, so an infrared camera is great because it allows you to see parts of the visible spectrum which you wouldn't be able to see with the naked eye. So that means that whether it's a sun or whether it's a person, you emit light at all different wavelengths. So what that's called, it's a black body spectrum. And what that allows us to do is actually measure the temperature from the color, right? So the surface temperature of our sun is around 6,000 degrees, so that means it's yellow. And then we can get the temperature just from the color. So that's a really important aspect of being able to do this kind of work, is understanding this physical relationship between color and temperature. So the hotter an object, it'll be bluer, and then the colder an object, it'll be redder. Right? So that means that objects in the top left corner will be really blue. So that means that they're going to be really hot, and very bright. That also means that they're very, very massive, which also means that they're not going to live as long as the sun. And then on the other side of the spectrum, we're going to have, in the opposite corner, we're going to have the red stars, which are slightly colder and older, but also less massive. And they will actually live a little bit longer than our sun. So stars over here will live maybe close to 10 billion years. So our sun is yellow, right? So it'll be right in the center, and it's right there. But of course, do you guys know what will happen to our sun as it dies?
As it's dying, it gets larger and it gets more red and darker.
Yeah, so it enters a red giant phase. right? And so what that happens is that if we catch a family portrait at the same time, so all the stars are there, they will be along something called the main sequence. And this main sequence means that a family of stars is born with blue stars, yellow stars, and red stars at the same time. But, as you guys have said, some of the stars live different lives, right? So our sun is now currently in its main sequence phase. It's yellow, and on that it fits nicely on that nice little strip. Then it'll become a red giant, and then it'll become a white dwarf, right? So, and that'll take about 8 billion years. So this then allows us to, that's just for one star, right? So the big blue stars live tens or hundreds of millions of years. The red stars will live even longer than ours. So if you catch this family portrait at different points in time, it'll look differently. So in order to do that, what we do is we take pictures. This is the family portrait of Omega Centauri. And then we separate them by color. And once you separate them by color, you can then put them on the HR diagram. And the really cool thing about this is that what you've measured now is the color and how bright they appear. Well, you know that stars like our sun will always be the same. So if you know how bright they appear, using something called luminosity, their luminosity measurement, if you know how bright they are and you know how bright they appear, then that tells you how far away they are. So the way this works is that the closer you are standing to a fire, the more you feel the heat energy. And that relationship holds for stars as well. So now you can tell how far away they are. And because you can see these different tracks, you can also tell the age of the stars. So the HR diagram gives us the age and distance of a family of stars, but it really depends on really understanding how a single star evolves, right? So those processes, how the evolution of a single star has something to do with stellar nucleosynthesis. And if we go back to the definition of our sun, it's a star that's got these nuclear processes, but we haven't really talked about nuclear processes, right? So have you guys heard of fusion? Nuclear fusion? That's a nuclear process. So what happens is that inside of stars, because it's such high great temperature and pressure, you can take two nuclei and join them together to become something else. So effectively how that works, you remember there's lots of hydrogen and helium. So one of the ways that you can create different elements, you can begin with 4 hydrogen atoms, and then you end up with 1 helium-4 atom. But of course, as you're doing this, you're getting other stuff as well. So you're creating different kinds of fuels. So as the hydrogen and helium ratio changes, you're getting different elements that become viable. And that's called the carbon, nitrogen, and oxygen cycle. And that means that you take carbon, nitrogen, and oxygen, protons, and you mix them, and then again you get some energy. And you can do this up until you get to iron. And the interesting thing about iron, and this will be kind of like the last science plot that I'll have, is that there's something called the binding energy, which means that it relates how hard it is to take apart different elements. So what happens with iron is that it's a very heavy. So on this plot, the blue line is where the iron line is, and then on the x-axis is just how many protons and neutrons make up the nucleus, and then on the vertical axis, the energy required to break them apart. And the way you can think about this is that whatever's to the right that has more protons and nuclei in the nucleus, you need energy in order for that to happen, and then whatever's to the left and whatever's to the other side, it releases energy. That energy comes back from a really cool equation, equals mc squared, and that additional energy is mass loss. So what happens is that once you start and you make these elements and you get to iron, you need actual extra energy in order to create more elements, which means that your nuclear processes are no longer supporting the gravitational collapse that's part of the definition of a star, right? So when that happens, you have a supernova. And when that happens, not only do you have this explosion, but all of the stuff inside of the star gets kicked out, right? So one of my favorite quotes from Carl Sagan is that we are made of stars. Have you guys heard of that quote before? So effectively what that means is that all of the iron in our blood is basically it was created in this fashion. So inside of us is the effects of supernovas, right? So if it wasn't for supernovas, we'd all be iron deficient. So thank God for supernovas. So that's kind of what I wanted to tell you guys about today is how the universe creates elements. So what we saw is that we can understand by taking the portrait of a family of stars, we can use the HR diagram to get the distance and the age of that family of stars. But in order to really understand that portrait, we need to understand how a single star evolves. And in order to do that, we talked a little bit about stellar nucleosynthesis and how elements really get created in the universe. Because the universe only started with hydrogen and helium and some traces of lithium, and then it had to create all the other elements that we see today. And the way that happened is through stellar processes like stellar nucleosynthesis and supernovas, which then ejected that material out into the universe. And of course, supernovas make for very beautiful pictures. So, if you guys have any questions, this is your time.